Hey everyone, welcome back. Today we're going to be diving deep into, something that sounds really complex but is actually incredibly cool, the Fast Fourier Transform,
Hmm.
or FFT for short. You might not realize it, but FFT is everywhere. It's kind of the engine behind things like Spotify, those filters you use on Instagram, and even some of the tech that helps doctors see what's going on inside your body with like MRI scans.
It really is foundational to a lot of stuff. And you're right, it might seem a little intimidating at first, but the core idea is actually surprisingly simple. So the FFT is all about understanding how any signal, whether it's, sound, light, or even stock market prices, can be broken down into a bunch of simple waves.
Okay, I'm intrigued. So is it kind of like taking a smoothie and separating it back out into its individual ingredients?
Yeah, that's a great way to put it. And by understanding these individual ingredients, we can analyze the signal in a whole new way. So this process of breaking down a signal like this is called the Discrete Fourier Transform, or DFT. But the DFT has a little bit of a problem. It can be really slow, especially when you're dealing with a lot of data.
So is it like trying to make that smoothie with a hand-cranked blender instead of like a high-powered one?
Exactly. And that's where the FFT comes in. It's like a turbocharged version of the DFT. It takes the same basic idea, breaking down the signal, but does it in a way that's unbelievably fast and efficient. The source material mentions that for a signal with like 1,000,000 data points, the FFT can be something like 1,000 times faster than the basic DFT.
Wow, 1,000 times faster. That's mind-blowing. So what's the secret behind this speed boost? Does it involve some kind of supercomputer or something?
Well, not really. It's all about clever math. The FFT uses this elegant concept called recursion. It's basically the idea of taking a big problem and breaking it down into smaller, identical problems that are much easier to solve.
So it's like instead of tackling a giant jigsaw puzzle all at once, you divide it into sections and solve each one separately.
Yeah, exactly. And then here's the really ingenious part. The FFT takes the solutions to those smaller problems and cleverly combines them to get the solution to the original, big problem. And it does this in a way that minimizes the total number of calculations needed, which is why it's so much faster.
From what I'm seeing in the source material, it seems like there are different ways to do this dividing and conquering. They mentioned something called radix.
Yeah, you're right. The radix basically tells you how many pieces you're dividing the data into at each step. So the most common FFT algorithm is radix 2, where you split the data in half over and over again.
I'm picturing this as like a tree with the original signal at the top and the data getting split into smaller and smaller branches as you go down.
You got it. But sometimes, depending on the type of data and the computer you're using, it might be more efficient to split the data into 3 pieces. That would be radix 3, or 4 pieces, radix 4.
So it's like choosing the right tool for the job.
Yeah.
You wouldn't, use a hammer to screw in a light bulb.
Exactly. And just like there are different tools for different tasks, there are different FFT algorithms optimized for different situations.
Okay, so we've got this idea of breaking down a signal into simpler waves using the DFT, and then the FFT comes along and makes that process super fast using recursion and different radixes.
Yeah.
I think I'm starting to get the big picture here, but how does this actually work in practice? I mean, what's happening inside the algorithm itself?
That's a great question. So it does involve a bit of math, but I promise it's more intuitive than you might think. Let's start with a simple example, let's say, of a sound wave. So think about a pure tone, like a single note on a piano. That pure tone, that single note on the piano, can be represented as a simple wave that oscillates up and down at a certain frequency. So that's its fundamental frequency.
Okay, so far so good. I can picture a nice smooth wave going up and down, yeah.
Now imagine, instead of just one note, you play a chord on the piano. That chord is actually made up of multiple notes played at the same time, right? Each of those notes has its own frequency, and when they're combined, they create a more complex sound wave.
Right, so the chords wave is kind of like all those individual note waves, like mashed together.
Exactly. What the DFT does is it takes that complex kind of mashed together chord wave and figures out what those individual note frequencies are and how strong each one is. It's like a mathematical prism that separates the combined sound wave back into its, individual frequencies, kind of like separating white light into a rainbow.
Okay, this is starting to make sense. So if we were looking at a graph of the chords wave, it might look all jagged and messy. But the DFT can show us that it's really just a bunch of simple waves kind of layered on top of each other.
You got it. And the FFT comes along and says, hey, I can do that separation way faster. It uses that recursion trick we talked about earlier, breaking the problem down into smaller chunks, Let's say our chord has 8 data points, representing the sound wave, over a tiny snippet of time.
Okay, so like 8 measurements of how loud the chord is at different moments.
Exactly. The radix to FFT would first split those 8 points into 2 sets of 4, then each of those sets into 2 sets of 2. And calculating the DFT for a set of just 2 points is super easy.
So we're at the bottom of that tree analogy now, looking at the simplest possible pieces.
Right. Then the magic happens. The FFT uses those simple 2-point DFTs and combines them in a very specific way using something called twiddle factors.
Okay, wait, twiddle factors.
Yeah.
That sounds a bit like something out of Alice in Wonderland.
I know. It's kind of a funny name.
Yeah.
These are complex numbers that basically help to shift and rotate the individual frequency components.
Okay, this is where I usually get lost.
Yeah.
Complex numbers. Twiddle factors.
I know it sounds a bit strange, but think of it like this. Those twiddle factors are like special ingredients that make the combining process work correctly. They ensure that when we combine those small 2-point DFTs, we get the correct 4-point DFTs, and then we combine those to get the correct 8-point DFT and so on, all the way back up to the DFT of the original signal.
So each step up that tree is like mixing ingredients together in just the right way to get the recipe right.
Yeah, that's a good way to think about it. The math gets a bit detailed, but the key is that those twiddle factors allow us to go from simple calculations on tiny pieces of the signal all the way back up to the full DFT in a really efficient way. That's the secret sauce of the FFT.
Okay, I'm following you so far. But if the FFT works best with powers of 2, like 8 or 16 data points, what happens if our signal has a different number of points? What if it has 10 data points?
That's a good question. In those cases, we can either pad the signal with zeros to get it to the nearest power of 2, or use a different radix for our FFT. For example, if we had 9 data points, we could use a radix 3 FFT, which would split the data into 3 groups at each step.
So we're choosing the radix that best fits the size of our data. It's all about being efficient.
Exactly. And there's another interesting aspect of the FFT. It can be applied to data in multiple dimensions.
Wait, multiple dimensions? I thought we were just talking about signals that change over time, like sound waves.
Yeah, you're right. That's the most common application. But think about images. An image is basically a 2-dimensional signal. It has brightness values that change across both its width and height.
Oh, okay, I see. So instead of just analyzing a signal over time, we can analyze it over 2 directions at once, like analyzing the colors in a painting or something.
Precisely. We can apply the 1D FFT to each row of pixels in the image, and then apply it again to each column. This gives us a 2D FFT, which allows us to analyze the image's frequency content in both directions. This is incredibly useful in image processing for things like edge detection, image compression, and removing noise from photos.
This is really blowing my mind. So if the FFT can work in 2 dimensions, could it also work in 3 dimensions, like with a 3D model or something?
Absolutely. In fact, 3D FFTs are used all the time in medical imaging, like CT scans and MRIs. They help doctors visualize the inside of the body in 3 dimensions and diagnose medical conditions. And in fields like scientific simulations, they can help us model and understand complex phenomena in 3-dimensional space.
Wow, the FFT is truly a multi-dimensional tool. But I have to ask, are there any limitations to the FFT? Is there anything it can't do?
Yeah, that's a great question. Like any tool, the FFT does have its limitations. One of the key assumptions of the FFT is that the signal you're analyzing is periodic, meaning it repeats itself over and over again.
Okay, so like a perfect sine wave that just keeps oscillating, up and down forever.
Exactly. But in the real world, most signals aren't perfectly periodic. They might have some repeating patterns, but they also have variations and changes over time.
Right. So if you tried to analyze a non-periodic signal with the FFT, would you get weird results?
You could, yeah. The FFT might introduce some artifacts or distortions because it's trying to fit that non-periodic signal into a framework that assumes periodicity. It's like trying to squeeze a square peg into a round hole. It might sort of fit, but it won't be perfect.
So it's important to be aware of those limitations and use the FFT appropriately. But even with those limitations, it seems like the FFT is an incredibly powerful and versatile tool. I'm curious, what are some of the other real-world applications where the FFT is making a big impact?
Oh, wow. Where do we even begin? I mean, we've already touched on image processing, audio processing, and medical imaging. But honestly, the list goes on and on. The FFT is used in telecommunications to transmit and receive signals, in radar systems to detect objects, in in financial modeling to analyze market trends, and even in, weather forecasting to predict future weather patterns.
Like the FFT is like the secret ingredient in so many different technologies.
It really is. Let's take a closer look at a few of these applications. Remember how we talked about the FFT being used for MP3 compression? Well, it's not just MP3s. It's used in almost all modern audio compression formats. It's the reason we can store, thousands of songs on our phones without needing a hard drive the size of a refrigerator.
It's amazing to think that this algorithm is changing how we experience music on a daily basis.
And speaking of changing experiences, think about those amazing special effects you see in movies. The FFT plays a huge role in creating those realistic explosions, those mind-bending visual distortions, and even those subtle filters that make actors look younger or older.
I never would have guessed that the FFT was involved in, Hollywood magic.
Yeah.
What about in the world of science and research?
Oh, it's essential there, too. Astronomers use the FFT to analyze the light from distant stars and galaxies, helping them understand the composition and behavior of celestial objects. Geologists use it to analyze seismic waves, allowing them to study earthquakes and the structure of the Earth's interior. And physicists use it to study the behavior of particles at the subatomic level.
Wow. It's like the FFT it's like a universal translator, helping us understand data from all different domains.
Yeah. That's a great way to put it. And what's even more amazing is that, the FFT is still an active area of research. Scientists and engineers are constantly developing new algorithms and finding, new applications for the FFT, pushing the boundaries of what's possible with this incredible tool.
Wow. So even after all these years, the FFT is still evolving and growing. It's amazing to see how one mathematical concept can have such a profound impact on so many different fields. So for our listeners out there who might be feeling a bit overwhelmed by all this talk of, algorithms and transforms, what's the key takeaway you want them to remember about the FFT?
Well, I think the most important thing to remember is that the FFT at its heart is all about making the complex simple. It allows us to take a seemingly chaotic signal and break it down into its, fundamental building blocks, revealing hidden patterns and insights that would be impossible to see otherwise. And it does this with, incredible speed and efficiency thanks to the beauty and elegance of recursion. So the next time you're listening to music or scrolling through photos or marveling at a scientific discovery, take a moment to appreciate the quiet power of the FFT working behind the scenes to make it all possible.
Beautifully said. It's a reminder that sometimes the most powerful tools are also the most elegant. Well, thank you so much for joining us on this deep dive into the fascinating world of the Fast Fourier Transform. I hope you all learned something new and exciting today.